All right, guys, we are starting chapter 16 in 1212. The PowerPoint, it can be found on D2L, or you can look in the shared class files. So this is all about acids and bases. Again, the beginning of the chapter, you need to read through that. Talks about the development of the theory around acids and bases, the historical context of, essentially, it was realized hundreds of years ago that there were classes of compounds that became known as acids, and there are other classes of compounds that became known as bases. They tended to share similar properties. We basically, over the years, there are multiple types of classifications that can be used. We're going to talk about some of those. That originally, they talked about things that are acidic in food tend to be things that are kind of sour. Things that are basic tend to be a little bit more bitter. They noticed that when soil is acidic, some plants, the flowers would grow to be one color. I think it's hydrangeas. At an acidic pH, the flowers are one color, and when the soil has a basic pH, the flowers are a different color. So it was just kind of recognized early on that these classes of compounds were very important in everyday life. And then over time, in the 1600s, the terms acid and alkali materials were developed to go beyond vinegar and ashes, which alkaline materials can be burned to make potash sometimes. So Robert Boyle did some tests on it. Again, I'm going to let you read the historical stuff, but when we get into, let's see, I'm going to skip over. So several different scientists developed different concepts, but the first one that we're going to focus on, there are two main ones that we rely on in what we do today. There's the Arrhenius model for acids and bases, and then there's the Bronsted Lowry model. Okay, everything up to this point in the slides have some familiarity with it, but I'm not going to test you on names or dates specifically until we get to this section with Arrhenius. So Arrhenius basically defined an acid to be a substance that when you dissolve it in water, it increases the concentration of hydrogen ions, which a hydrogen ion is an H plus ion. Although when it's in water, the H plus ions do not float around freely. They tend to get connected to a water molecule, meaning a lone pair of an oxygen, which is a partial negative, is attracted to an H plus, and it ends up forming a coordinate covalent bond where the lone pair forms a bond to the hydrogen and turns it into an H3O plus. Okay, so a hydrogen ion in solution exists as a hydronium ion. All right, so just know the connection. We'll kind of use those two things interchangeably in this section. So acids will cause an H plus to be formed in solution, or I could say acids cause a hydronium ion to be formed in solution. Okay, example of an acid, HCl, HBr, HI. There are lots of different molecules that we could refer to. Most acids, we can recognize them. They're written with a hydrogen in the front and then some anion in the back, so that when it splits, I would get the H plus coming off and then a Cl minus. You do have some acids like acetic acid is what's called a carboxylic acid. That's a class of organic molecules where typically acetic acid, we usually write CH3COOH is how the structure is written in organic. In that case, it's the last hydrogen is the one that can break off as H plus. Again, all those compounds are kind of written in the same way. So if you see one where the hydrogen's in the front, that's likely to be an acid. Or if you see an organic molecule involving carbons that ends with COOH, that's a carboxylic acid as well. Okay. So, and sometimes the fact that it ends with OH, people think it's a base, but when we see that COOH, that's a carboxyl group. It's kind of a trademark structure in organic, and it does behave like an acid. All right, then a base is something that when you dissolve it in water, it increases the concentration of hydroxide ions. Okay, so that is how Arrhenius defined an acid and a base. That's a pretty straightforward definition of both. You definitely need to be familiar with that. But then there's two guys, Bronsted and Lowry. They came up with a little bit broader definition where an acid is a proton donor. Again, a hydrogen ion. If you think about a hydrogen atom, it has a proton in the nucleus, an electron flying around it. If it forms an H plus ion, we take the electron away, so all that's left is a proton. So an H plus ion is also called a proton. So something that can give up an H plus ion is an acid. And then a base, and with that, we do get a few terms that come from that. If an acid is monoprotic, that means it can give up one H plus ion. If it's diprotic, it can give up two H plus ions. If it's triprotic, it can give up three. If it's polyprotic, that means it can give up more than one. 2, 3, 4, however many. So here's some examples that you should know. You should recognize all those. A base is defined to be, it can be a hydroxide donator, okay, but more broadly, it can also be a proton acceptor. Okay, now this definition is going to include the Arrhenius bases, but it's going to add another class of them where, like ammonia, the way it behaves when ammonia reacts with water, the ammonia itself can take a hydrogen from the water molecule, and the ammonia, when it gains a hydrogen, becomes the ammonium ion. So it goes from NH3 to NH4+. When it does that, the water molecule is converted into a hydroxide. So ammonia is acting as a base by taking a hydrogen from water, which causes a hydroxide to be formed. So this is a little bit more of a detailed definition than the Arrhenius definition of a base. Now our bases, we should recognize them as the two types of bases. We can have metal hydroxides. Now, for a metal hydroxide to act like a base, it has to be able to dissolve into solution. So hydroxides are not all soluble. This is a place where you kind of need to know your solubility rules and realize that alkali metals are soluble with hydroxide, so group 1 metals, sodium hydroxide, potassium hydroxide, lithium hydroxide, and so on. And then the bottom of group 2. Usually specifically strontium and barium hydroxide, they are soluble in water, so they dissolve and they are strong bases. Above strontium, calcium hydroxide, sometimes it's included as a strong base. The problem with it is it's only a little bit soluble. So it's kind of borderline. If it's only slightly soluble, do you include it or do you not? It kind of depends on the book you're looking at. Okay? But the group 1 metal hydroxides and the bottom of group 2 metal hydroxides, those are our strong bases that we definitely should recognize. And then ammonia is a base. Again, I described how it behaves a minute ago. And then there's a class of organic molecules where if I take ammonia and replace one of the hydrogens with a carbon group, like a CH3 or several carbons, then that group of compounds, they're still going to behave like ammonia, but we call them as a group, they're called amines, A-M-I-N-E-S. The amines are a group of organic molecules that contain nitrogen, but they behave like ammonia does in solution. All right, and then here's a reaction, just because that ammonia thing is a little bit different from what people usually have seen. But if I put ammonia in water, when they interact, the ammonia takes a hydrogen from the water, making it NH4+, and then the water becomes a hydroxide. Okay? The formation of that hydroxide is going to make the solution basic. All right, now, again, in this concept of Bronsted Lowry acids and bases, it introduces an idea that basically some molecules are capable of acting like an acid or a base. It depends on the circumstances. So water, sometimes in solution, is going to give up a hydrogen. Sometimes it's going to accept a hydrogen. If it can go either way, the word for that is amphoteric. Okay, it's in the book, amphoteric. It's a molecule that can act like an acid or a base, kind of like if I can throw baseball with my left hand or my right hand, there's a word ambidextrous that I can use either hand. Same idea with acids and bases. A molecule that can do both is amphoteric. Okay, one more example of that, kind of the same derivation. An amphibian is something that can live in water or on land. So again, if you have that alternative, that's amphi or ambi are the words, the prefixes. So when molecules either gain or lose hydrogens, we need to kind of connect what the structure of the molecule is before, and then when it either gains or loses a hydrogen, what does it become? We call that pair of things, it's a conjugate acid-base pair. Okay, so let's define that a little more closely. And again, amphoteric, that's something that can be an acid or base. So if I look at the reaction just in water itself, this is a reaction called the autoionization of water. I'd say, okay, in a beaker of water, the molecules are always bumping into each other. Most of the time when they bump into each other, they just bounce off and kind of float off into solution. But every once in a while, there will be an acid-base reaction between two water molecules. Okay? Now what happens when they bump into each other, let's just say the lone pair of one oxygen atom is going to attract a hydrogen of the other water molecule, pulls the hydrogen over. So one of the waters is going to be giving a hydrogen away, so it's a proton donor. The other hydrogen is going to be accepting a hydrogen, so it's a proton acceptor. Okay, so one's going to be acting like a Bronsted Lowry acid, the other one's going to be acting like a Bronsted Lowry base. When that happens, I end up with a hydronium and a hydroxide. Now, this reaction doesn't happen a lot in water because when I look at stability, the two water molecules are very stable. They don't break apart very often. And then when I form these ions, I mean, they're okay, but they're not as stable as water is. So if I evaluate this equilibrium, again, it is an equilibrium reaction, basically when my when my reactants are really stable, it should make sense that the K value for this reaction, which this is a specific reaction called the autoionization or self-ionization of water, because there's nothing present but water. The K value for this reaction is 1 times 10 to the minus 14. So what that tells me is when K is that small, it tells me that most of the molecules are going to be in the form of the reactants. I'm going to have very little of the products in solution. Okay? Now, if I write up the expression, Kw equals the products on top over the reactants, if you notice my reactants are both liquids, so in the bottom there will be no molecules down there that are shown in the expression because solids and liquids don't appear. So my expression is going to be Kw equals the H2O concentration times the OH concentration. Okay, my two products multiplied together in the numerator, that's all I have for the whole expression. We know that Kw is 1 times 10 to the minus 14. So from that equation, which is an important equation that you need to know, from that equation, I can actually solve for the concentration of hydronium ions and the concentration of hydroxide ions that would exist in water at any given point. Okay? Now this is specific. K values are always tied to a temperature. So we're looking at 25 degrees Celsius, which is normal room temperature. So we're going to solve. Since this reaction produces 1 hydronium for every 1 hydroxide, that means that in pure water, these two values have to be equal to each other. Okay? The H3O and the OH minus are equal to each other in pure water because I can't form one without forming the other. Well, if I just plug in, let's just say that the concentration of H3O is X. That means hydroxide is also X. I plug in Kw equals X times X to get 1 times 10 to the minus 14. Essentially, X times X is X squared equals Kw. If I just take the square root of both sides, that tells me that the hydroxide concentration is 10 to the minus 7 molar, and the hydronium concentration is 10 to the minus 7 molar. It's just the square root of the Kw value. So, in water, pure water, the H3O and the OH concentration are equal. Okay? Now, when we define a solution to be either acidic, basic, or neutral, what we're looking at is the ratio of the H3O to the OH concentration. When they're equal, the solution is not acidic or basic. If the H3O concentration is high and the hydroxide concentration is low, H3O is the acidic ion in water. Hydroxide is the basic ion in water. So if I have a lot of H3Os, the solution is going to be acidic. If I have a lot of hydroxides, the solution is going to be basic. And if they're equal to each other, then that's going to be a neutral solution. Now, that will tie into pH, which we're going to do in a few minutes. But the pH is going to be the negative log of the hydrogen concentration. In neutral water, the hydrogen concentration is 1 times 10 to the minus 7. If I do the negative log of that value, the pH of pure water is 7. Okay? So, pure water, they're equal. It's a neutral solution. But when we add something to the solution, if we add something that increases the hydronium concentration, that substance that I've added is called an acid. It's going to make the solution become acidic. If I add a base to the solution, a base is going to produce hydroxides. If I have more hydroxides in solution, then that's going to be a basic solution. If you add a base, the solution becomes basic. Okay? So acids and bases are compounds that mess up. Remember, in pure water, H3O and OH are equal to each other. If we add something that breaks up that balance, that's what acids and bases do. Now, as you can see when you read the equation, if Kw equals H3O times OH, that means the two ions have to be inversely proportional, because K is a constant, 1 times 10 to the minus 14. H3O and OH, the product of those two values has to equal the constant. So if I do something that makes one of the numbers go up, the other one has to come down so that when I multiply them, I'll still get the same value. Meaning if I double H3O, I have to cut hydroxide in half. Therefore, when I multiply them together, it'll still equal 1 times 10 to the minus 14. You could never have a solution where both of them go up. Because if they both go up, when I multiply them together, it won't equal K anymore. All right? So, when we look at a solution, in pure water, we know that H3O and OH are both 1 times 10 to the minus 7 molar in their concentration. If I do something that makes the H3O concentration go up, so if the H3O concentration becomes greater than 1 times 10 to the minus 7, the hydroxide has to go down so that only one of them could ever be greater than 1 times 10 to the minus 7. The other one has to be less than 1 times 10 to the minus 7. Okay? So basically, if I know what one of them, if I know its concentration, then I should be able to tell if it's greater than 1 times 10 to the minus 7, the other one's got to be less, and therefore the one that's greater is going to tell me whether the solution is acidic or basic. So when H3O is greater than 1 times 10 to the minus 7, I know that the solution is acidic. If the hydroxide is greater than 1 times 10 to the minus 7, the solution has to be basic. Now, a little review from 1211. When we learned types of reactions, we learned several reactions that can involve acids and bases. First of all, the most basic one, a neutralization reaction. If I make sodium hydroxide with nitric acid, it's essentially a double displacement reaction. When we swap partners, when we do an acid plus a base, we get a salt and water. If the salt is aqueous, then if we wrote the total ionic equation, we would break up, remember, strong bases, or any ionic compound, when we dissolve it, should be broken into ions. A strong acid will also break into ions, so nitric acid becomes H plus and NO3 minus. When we have all these ions in solution together, the H pluses and OH minuses, they're going to come together to form a water molecule. So basically everything else is broken up in the reaction except for the water. So then when I start canceling out my net ionic equation, the sodium is going to cancel, the nitrate is going to cancel, they're just spectators. My net ionic is going to be OH minus plus H plus yields water. Okay? Hopefully you can see that. Again, it's kind of an important concept. The acid brings the H plus, The base brings the hydroxide. When they neutralize each other, I'm making a water molecule. All right, so acid-base pairs, we mentioned this before, the conjugate acid-base pairs. Essentially, when molecules gain or lose hydrogens, we need to recognize which ones are related to each other. So on this slide, I see a reaction where HF, which is called hydrofluoric acid, reacts with water. Basically, the acid is going to give away a hydrogen to the water molecule. So the HF is the proton donor. The water is the proton acceptor. Okay? So you need to be able to identify which one's the acid and which one's the base. That's important. Then I look and say, okay, well, the HF, its job is to give away a hydrogen. Once it gives the hydrogen away, what's left? Well, with HF, if I take away the hydrogen, it leaves me with F minus. So it's kind of important to realize HF and F minus, they're related to each other. Okay? If HF loses a hydrogen, it becomes F minus. Well, this is a reversible reaction. So what if F minus gains a hydrogen? Then it'll turn back into HF. So while this one is behaving as an acid to make the reaction go from left to right, fluoride, if it accepts a proton from the solution or from something else in the solution, when F minus accepts a proton, it can turn back into HF. Well, accepting a proton is what a base does. So while HF is an acid, F minus is a base. We always call the things on the left side are the acid and the base. The things on the right side are the conjugates of my acid and base. Specifically, my acid has a conjugate base. And then when I look at water, water is behaving as a base. It's accepting hydrogen. It becomes hydronium. So again, those two are related to each other. They are a conjugate acid-base pair. If this is a base, then the other one must be the conjugate acid. They're always going to be opposite of each other. If the first one's a base, the second one's an acid. If the first one's an acid, the second one's a base. Okay, so we define a conjugate acid-base pair to be two things that differ by the gain or loss of a hydrogen. Going one way, you lose a hydrogen. Going the other way, you gain a hydrogen. But a conjugate acid-base pair is always separated by a single hydrogen. So if I look at this one, again, ammonia plus water yields the ammonium ion plus hydroxide. If I said label the acid-base pairs, you look at your reactants and say, okay, the water is going to give a hydrogen to ammonia. So water is the acid, ammonia is the base. Okay, label that first. The acid and the base are always on the left side. On the right side, I have conjugates. So if ammonia is the base, ammonium is the conjugate acid. If water is the base, well, in this case, water is the acid, then hydronium is the conjugate base. The acid has a conjugate base. The base has a conjugate acid. Okay? So make sure you do that. Mastering chemistry will make you practice as well. All right, so conjugate acid-base pairs differ by a hydrogen. They can convert back and forth between the pair. And then their relationship is, so NH3 and NH4 plus are an acid-base pair. NH3 is a base. NH4 plus is the conjugate acid. Their strength of their ability to behave like an acid or base, again, in 1211 we introduced the idea of strong acids and weak acids. Whether something is strong or weak tells how well it can, like a strong acid will always give its hydrogen away. So it'll always give the hydrogen away and exist in the form without the hydrogen. Okay? A weak acid is not very good at giving its hydrogen away. So most of the time the hydrogen is going to stay attached. Only a few molecules of a weak acid will be able to give its hydrogen away at any given point. Okay? So, if a base is weak, then its conjugate will be stronger. The weaker the base, the stronger the conjugate acid. If I have an acid, the weaker the acid, the stronger the conjugate base. Okay? So the strength of a conjugate acid-base pair, they're inversely proportional to each other. A really strong acid will have an extremely weak conjugate base. A weaker acid will have a stronger conjugate base. Okay? So it's always a balancing act between those two things. And what do we mean by strong and weak? It's how efficiently an acid or base will either give a hydrogen away or accept it. Strong acids and bases are really good at giving away all of their acidic hydrogens or accepting all of their hydrogens. Okay? So a very strong acid has a strong tendency to give up a proton. Specifically, of all the acids that can exist, there are 7 of them that are listed. Again, it's going to come up on a slide. There are 7 of them that are classified to be strong acids. And those are the ones that we pretty much just say they completely ionize. They give their acidic hydrogens all break off. Okay? And they are 100% dissociated in solution. Okay? A strong base will 100% break up, like sodium hydroxide. It'll give up, like if I put 100 of them in solution, I'll get 100 Na pluses and 100 OH minuses floating around in the solution. All right, I think that's a good place to cut off. We're starting to run long in this video. We'll do some more in a bit.